Welcome everybody, and congratulations, you are attending the best session of the conference. I'll be your session chair for this session. My name is Daniel Zilasko, and without further ado, because we are schedule tight and I don't want to take away any minutes from the authors, we'll have our first presentation about TouchWalker, real-time avatar locomotion from touchscreen finger walking, and our presenter will be Gunther Park. I hopefully did. Sort of.
Thank you for introduction. My name is Gunther Park, and today I will present our work, TouchWalker. On touchscreen devices, a virtual joystick is commonly used. While widely adopted, this interface may not fully leverage the expressive potential of touchscreen interaction. Moreover, the lack of tactile feedback in virtual joysticks may limit users' sense of embodiment and immersion. Fingerwalking is a way of mimicking footsteps by finger gestures. We explore this because fingerwalking could leverage rhythmic by finger gestures to evoke the sensation of foot-ground contact, so it can provide rich temporal and spatial cues for avatar control, and it also enables a more embodied and tactile interaction method for touchscreens. We propose TouchWalker, a real-time system that enables expressive full-body avatar control through fingerwalking gestures on a touchscreen. For this, we reconceptualize fingerwalking as a continuous and expressive input modality. TouchWalker has two components. First, TouchWalker MotionNet, a real-time neural motion generator, and TouchWalker UI, per-frame avatar control UI on touchscreens. We conduct a user study comparing TouchWalker to a virtual joystick baseline. Prior works on gesture and touch-based locomotion are mostly rely on symbolic gesture or fingerwalking, but they are limited to the playback of predefined motions. This leads to a lack of real-time responsive motion generation. Some work suggests that body-based and tactile interactions can enhance immersion and engagement in virtual environments, but no prior work combines touch-based fingerwalking with real-time full-body motion generation. This is a demonstration of our system. Our system allows to generate continuous frame-by-frame full-body locomotion for fingerwalking. It improves embodiments, enjoyments, and immersion through combining tactile immediacy and neural motion generation. First, we introduce our framework, TouchWalker MotionNet. It comprises two main components, TransNet and PostNet. TransNet predicts the next translation from the movements of the user's touch input and the character's translation history. PostNet generates the next pose from the user's touch input, the character's state history, and the target direction. This is our loss function. The loss function consists of reconstruction loss, forward kinematics loss, direction loss, context loss, and context transform loss terms. For more detail, please refer to our paper. Next is TouchWalker UI. Our UI has a touch region which displays a top-down rendering of the ground beneath the avatar. In this region, touch position is interpreted as the contact foot position relative to the avatar's coordination on the ground. Touch region has two lines, a red vertical line showing the avatars for direction and upward horizontal line for lateral alignment. In user study, we compare two conditions, our method, touch worker, and virtual joystick as the baseline. Touch worker consists of a touch worker UI for movement and a joystick for orientation. And virtual joystick consists of dual analog virtual joystick for orientation and translation each. We formulated the following hypothesis. First is touch worker will lead to higher ratings of embodiment, enjoyment, and immersion compared to the virtual joystick. Second is the difference in subjective ratings between touch worker and the virtual joystick will be influenced by participants' prior joystick experience. For our user study, we designed two tasks. First is multi-stage navigation. In this task, users have to pass through a course with 5 stages. First is hole avoidance. In this stage, falling into holes returns to the start. Second is speed control, which composed of 2 parts. In strong wind part, participants must move above a certain speed, and in the speed limit part, participants must move below a certain speed. Third is narrow path. Participants pass through a narrow and winding path. The next is foot buttons, which requires activating 5 buttons one by stepping on each. Last is rolling obstacles, where rolling balls coming down a slope. Second task is stepping stones, which requires crossing the river without touching the water. Stones and wooden planks as the only traversable surfaces. Wooden planks gradually sink upon contact. A total of 14 participants were recruited. The post-test questionnaire consists of 11 items selected from EQ, IMI, and IEQ. By user ratings result, touch worker achieved significantly higher ratings across all 3 dimensions, and touch worker shows higher medians and narrower ranges. These results support our first hypothesis. To further assess potential group level effects, participants were split into low and high experience groups based on their self-reported virtual joystick familiarity. The results revealed non-significant differences across all 3 dimensions, and effect size also small across all measures. These results show that second hypothesis is not supported, and the conclusions from the 2 hypotheses indicate that touch worker outperformed virtual joystick in all 3 dimensions, regardless of prior joystick experience. Completion time and non-time performance results show that while virtual joystick is generally faster, touch worker allows for more consistent execution. Participants reported embodiment was enhanced when describing finger working as rhythmically aligned and direct mapping to footsteps. But some reported a sense of disconnection when they felt the avatar did not respond as intended. Several users generally found enjoyment from the novelty and fun of describing the working gesture, but some mentioned that input difficulty or unfamiliarity. Users feel more immersive and cognitively engaging due to the need for continuous focus and physical coordination. And in addition, there were mixed views on intuitiveness and learnability. TouchWalker was praised for precision and the virtual joystick for ease of control. And some participants suggest the use of TouchWalker in puzzle, stealth, and platformer games. Our study results confirmed that TouchWalker outperformed the virtual joystick across all subjective dimensions. We found no significant effects of joystick familiarity on the preference for TouchWalker. And TouchWalker was more consistent and precise in deliberate control, but in obstacle-heavy and spatially constrained tasks, virtual joystick was faster. TouchWalker holds promise for integration into games, emphasizing deliberate movement and immersion, while it needs improvement in directional responsiveness and reducing input effort and fatigue. In conclusion, we have introduced TouchWalker in this presentation, a real-time touchscreen locomotion system. As our user study, TouchWalker significantly improves users' sense of embodiment, enjoyment, and immersion, regardless of prior joystick experience. It shows advantages in tasks requiring precise and deliberate foot placement tasks, but challenges remained in spatially constrained or rapid response scenarios. Our findings suggest that TouchWalker offers a promising alternative for expressive out control. Oh, sorry. This is the end of my, This is the end of my presentation. Thank you for listening.
Yeah, thank you very much. We have time for a couple of questions. If you have any, please stand up and use the standing microphones. When you can't move, just tell me, I come over with the mic. Any questions from the audience? Otherwise, I can start. You talked about, I think it was your hypothesis too, that the familiarization with dual analog stick might have an effect or should have an effect here. I agree. To which extent do you think you were not able to confirm the hypothesis, but I also have noticed that the subgroups were very small. So do you think the power was high enough to actually analyze this hypothesis?
Sorry.
So given that the subgroups with the familiarization to the joystick interface was very small, I wonder if the power was too small to analyze hypothesis 2. What do you think about that? We maybe can also have that on offline. A comment to everybody: when you have any additional questions, we have this Discord channel. Please feel free to add your questions there. Is there any other question from the audience? Otherwise, yeah.
Thanks for the session. What about the fatigue? I mean, looks like if a user kind of plays a game like an hour, like a virtual joystick, you just one finger and then you just keep walking. But this one, you have to continuously use your 2 fingers. Did you have any study on the kind of fatigue over time?
Thank you for your questions. We didn't about the fatigue, how long users can finger working, but may- it's all our thing is on 15 minutes or 30 minutes. How about that? Some users saying that it's little fatigue. They feel little fatigue on touch finger working, but we didn't study about that. Oh, sorry. Thank you.
Yeah, so let's thank the author again, the speaker again, for the great presentation. So the title of the talk will be Isometric and Elastic Balance Boards for Virtual Reality Locomotion. And Michael will have the talk. Thank you.
Hello everybody. I am Michael Nelson from Purdue, and today I am presenting Isometric and Elastic Balance Boards for Virtual Reality Locomotion. So locomotion is central to how users perceive immersion, spatial orientation, and overall user experience. Traditional methods like joystick and teleportation can cause spatial disorientation, reduce presence, and induce motion sickness. And motion sickness is frequently attributed to postural instability or unexpected vection, which embodied systems like the one we explore in this paper can help mitigate. So the embodied system we looked at are balance boards, specifically center of balance-based devices, which enable users to control their movement by shifting their body weight. These come in two varieties, isometric, which are boards that do not have any repercussive feedback, and elastic, which does have resistive feedback. So we are interested in how these devices are used. So the factors we're looking at are how do feedback and orientation when using these devices affect their movement behaviors, user experience, and motion sickness. The paper is a 2x3 within group design with feedback looking at isometric and elastic boards, and orientation, which looks at conditions virtual, physical, and conditional virtual, which I will explain shortly. The application, we have two custom balance boards, both styled after a skateboard, which the application reflects. Both of these have 4 load cells in their cardinal corners, and the elastic balance board has 4 time-of-flight sensors and a gyroscope to measure rotation. And this was made with Unity and MetaQuest in Link mode. So I should probably talk about how the device works to explain the conditions. So when the user leans in a direction, in this case forward, in the virtual condition, they will rotate the board. In the physical condition, they will translate in that direction. And in the conditional virtual condition, they can toggle between these two modes at will. Similarly, if they lean backwards, this will rotate in counterclockwise position in the virtual condition, translate in the physical condition, and toggle in conditional. When leaning to the left or to the right, the board will translate just like you would expect a skateboard to do in the real world. So these are the conditions in action. So the physical board is aligned with the input device that they are standing on. The virtual board is able to rotate, so it is not aligned with the input device. And in conditional virtual, they can toggle between these two modes. So for participants, we had 28 participants, 18 male, 10 female, all around college age, most of whom had prior VR experience, and about a third had prior board sports experience. So that'd be experience with skateboard, surfboard, etc. The environment that the participants navigated through is a 1/12 scale model of the Indianapolis Motor Freeway, which is a course that has numerous right and 45-degree angle turns. For the movement data, we collected trajectory length, the speed, the average speed at which they traveled, the time it took them to complete the trial, the root mean squared error, which is the error from the deviation from the center of the spline used to represent the path, and the sway velocity, which is the average velocity that the user's head moves. For self-reported metrics, we have system usability, presence, NASA task loader, intrinsic motivation, motion sickness, and a preference ranking, where lower numbers are more preferred and higher numbers are less preferred. So in terms of results, and here's just a little guy moving. For movement behaviors, the virtual condition was found to be, to have traveled less than the conditional and physical conditions. In terms of time, physical was found to be faster than the conditional and virtual conditions. So consequently, the speed was faster in the physical condition. For root mean squared error, the isometric board resulted in higher error, so the elastic board was more accurate for this navigation task. And for sway velocity, the physical condition was found to be have less than the conditional and virtual conditions. In terms of self-reported metrics, for presence, we did not find main effects, but we did find an interaction effect where physical orientation produced lower presence for the than the virtual and conditional under isometric feedback. For interest, we found that participants were more interested in the virtual condition than the physical condition. For motion sickness, under virtual and conditional conditions, elastic produced lower sickness than isometric modes. For preference ranking, we did 3 rankings, one for each of the conditions and one combined one. We found that participants preferred the elastic board and in the virtual orientation. So from our data, we found that orientation in which this device is used strongly influenced the efficiency, shaping the trajectory and the trajectory length and speed, while feedback influenced the accuracy while navigating through this task. For user experience, we, while there were no significance for usability, they all were rated as quote-unquote good. Presence was showed some congruent sensory motor pairings to strengthen immersion. Workload scores were were low in all conditions, suggesting that this should have suitability for extended sessions. Participants also expressed clear preferences for the elastic and the virtual orientation modes. For motion sickness, known main effects were found for orientation or feedback alone, but there was an interaction effect where elastic feedback reduced sickness in the virtual and conditional orientations. These results support the postural instability theory that restoring forces can help stabilize balance and reduce comfort. So there are some limitations we should address. The Elastic board is suspended by springs, so there is about a 3-inch difference in the height, which may have influenced comfort and performance. We also had an uneven gender distribution, which may limit the generalizability across demographics. Most participants had prior VR experience, which could have affected their performance and sickness results, and no correlation was found between sway velocity and reported motion sickness, which is something to further investigate. In conclusion, orientation shapes the efficiency metrics, while feedback influenced accuracy. Elastic feedback reduced motion sickness under certain conditions, and usability was consistently rated as good across systems, with participants preferring elastic feedback and orientation. In future works, we plan to address board standardization, explore a more diverse range of terrains and locomotive tasks, broaden the participant demographics, and investigate sway velocity as an objective measure for motion sickness. Thank you for your time.
Yeah, thank you very much, Michael. You were early, so we have a lot of time for questions. Any questions from the audience? There's one.
Thank you very much for your nice presentation. I wonder, was there any delay between display and reality? Sometimes the cyber sequence is made by the differences between the visual stimulation and real feedback.
There was not much delay. If you're talking about the acceleration in the physical thing, or there was not.
When you turn right or when you go forward, then the screen should move like that.
Yes.
Right?
Mm-hmm.
But what was the discrepancy between display and real thing?
There was not much. If you're looking for megahertz, I have to look back at the paper.
In reality, when you use HMD, if there is 20 millisecond differences,
Yes.
then it will cause cyber sickness. That's why I'm asking you.
Yeah, I believe we reported in the paper, but it was low, and none of the participants reported issues with movement. But I can, yeah, I'm sorry.
Okay, my second question is, subject could be a different because there should be a inter-subjective difference. So when a subject is very sensitive to cyber sickness or real motion sickness, then he will or she will say it's horrible or not. So did you measure whether how much they are sensitive to motion sickness?
We did not know.
Okay, thanks.
Thank you.
Yeah, I think that was not the center of the study, and I also would always encourage not to mixing up interaction studies with cyber sickness studies, but that's a completely different topic for a different type. Any further questions from the audience? I maybe have a question. Maybe you referred to that, but you said that 1/3 of the sample had some prior experience with board sports,
Yes.
Especially the others. Were there any fear of falling over, tipping over, something like that, or were they all comfortable?
You're talking about specifically with people who had board sports experience?
Both groups are interesting, but I think the ones with experience were not afraid maybe of
Yes.
falling over.
Not generally. There were some people who were afraid, but we did have a safety mechanism to make sure they didn't fall. But yes, there was not much fear of falling over.
Okay. Yeah, and no difference with either springs or no springs. So
Yeah.
how stiff were the the
So
springs?
we limit the rotation of the elastic board to 8 degrees mechanically. So that's for safety reasons
Yeah,
to
yeah.
prevent them from not falling.
Okay, yeah, great. Any other question? Oh, there's one. A last one.
Thanks for the great talk. I noticed that the perceived load results are pretty low for most conditions. And I was just wondering, like, maybe if like the task environment itself, like the difficulty of the turns, like the speed at which the turns are supposed to be made, are maybe a bit easier for participants overall, so that the difference between like conditions isn't that much. Maybe if like the task itself was a bit more difficult, I guess, in terms of orientation, that could introduce more instability and make more difference between conditions.
Yeah, that's a interesting thing to raise, and I think that's something that I will have to investigate in future studies.
Yeah, great. Let's all thank Michael again. The title of the presentation is Exploring Pointing and Confirmation Techniques for Teleportation Across Varying Elevations in Virtual Reality. And Khaled will have the presentation. Thank you.
Thank you very much for the introduction. Good afternoon, everyone. My name is Khaled Hassan, and I'm an associate professor in computer science at UBC's Okanagan campus. Today, I'm going to present a paper titled Exploring Pointing and Confirmation Techniques for Teleportation Across Varying Elevation in Virtual Reality. Now, teleportation is a very common locomotion technique that allows users to move from one location to another location in virtual environment. Especially useful when you have limited physical space, but you want to navigate to a large virtual world. Traditionally, teleportation commonly relies on the handheld controller or the physical controller. However, with the advancement of head-mounted display, currently it also provides controller-free hand-based teleportation as an alternate solution. For instance, this is one of the papers we published in ISMAR 2022, where we explored how actually we can leverage the wrist movement for teleportation in virtual world. So with the hand-based teleportation, the task is commonly divided into two sub-activities. The first one, we have to point to a destination, and once we point to a destination, the second subtask is perform a selection action to teleport to the destination. Now, for instance, in this image, as you can see, the user is pointing to, like with their left hand, and like on the left image, and on the right image, like you can see that the user is performing a pinch gesture for the confirmation to teleport to the destination. Now, apart from on-device hand tracking capabilities, recent head-mounted display also provides the capability such as head tracking and eye gaze tracking. For instance, user can now move their head to point to an object or look towards an object to interact with it in the virtual environment. Also for teleportation, researchers looked at two different styles of teleportation ray. Parabolic, as you can see from the left image, and linear, as you can see on the right image. Previous work mostly focused on different style of teleportation ray, but for flat surfaces, with only a few studies that actually explored the use of different teleportation pointing technique on different elevated spaces. For instance, Skyport is one of the earlier work that compared linear and parabolic pointer with controller, and they found that the linear pointer is faster and more accurate than the parabolic one. However, this particular work they actually make the comparison with a handheld controller, but did not include any controller-free method, such as hand, head, or gaze. Since navigation in elevated space, such as in staircases, in balconies, or even different platforms, is common in virtual environment, there is a need to understand users' performance of different pointer types when teleporting to elevated spaces. Therefore, we conducted a user study where we explored different controller-free pointing techniques for teleportation. More specifically, what we did, we explored a set of pointing technique with eye gaze, hand, and head, each combined with two different pointer style, linear and parabolic. Note that as you can see here, the left bottom corner is empty. So what we did basically, we removed the parabolic version of the gaze-based pointing after a pilot study where participant mentioned that this form of pointing led to high level of confusion and discomfort. As mentioned before, teleportation, it requires a confirmation action as the final step to be teleported to a particular destination. Therefore, based on the prior work, we included 4 different confirmation techniques. Those all are controller-free, such as finger pinch, dual, eye blink, and voice as 4 different options. So considering this confirmation technique with different pointing technique opens up an interesting design space, especially when users need to teleport to upward or downward, not just on a flat surface. So the goal of this paper is to explore a set of pointing technique and confirmation technique for controller-free teleportation across varying elevations in virtual reality. Now I'm going to talk about the study that we conducted. So for this study, we used a task where users are required to teleport from one platform to another platform, varying different distances and elevation. For each trial, participants began with pointing to a blue cube placed in front of them and perform a selection action to start that trial, which, as you can show on the left image, this was specifically done so that all the participants started from a constant initial location. Once they aim at the spherical target, which you can see on the right image, they have to perform a confirmation action. Now I'm going to show you a set of videos with the pointing and confirmation technique that we used in our study. We'll first look at different selection or confirmation technique, and then we'll look at different pointing technique. So in this video, we are using finger pinch for selection with gaze linear. For finger pinch, as you can see, user can use their dominant hand, in this example, the right hand, to perform the selection action. In this video, they are using the eye blink for confirmation with gaze linear for pointing. We use the single eye blink in this study to avoid any accidental trigger from unintentional eye blink. Also, we use the right eye blink for confirmation and the left eye blink for pointing, so that like the pointing and confirmation, they actually do not interact with each other or impact the performance or affect the performance of each other. Here is another video showing gaze linear with dual, where users are required to hold the pointer steadily within a certain angle for 800 milliseconds to be teleported to a destination. Here, note that dual, they do not require any extra action such as pinch, thus reduce physical effort. However, there are an additional wait time, which can make the task completion time longer. Here is another video with gaze linear with the voice as a confirmation technique. Here the user is using the gaze to control the ray, and for confirmation they had to say the word go to teleport to a destination. So they point to an object or point to the sphere and they have to say the go word. So these are all 4 confirmation techniques that we used in our study. Now I'm going to show you videos with the pointing technique that we used in our study. So this is a video where we use the hand linear for pointing and pinch for selection. Note that the pointing was done with the dominant hand and pinch was done with the non-dominant hand. This was specifically done as if, like is one of our earlier work, we found that like people prefer to use the dominant hand for fine-grained action, such as like controlling the pointer, and left hand for coarse-grained action, which is kind of making a selection, which also follow the Gerard's theory of bimanual interaction. This is another video where we used hand parabolic and again confirmation with the finger pinch. Like this one is another video where we use the head linear with the finger pinch. For the head linear, the pointing ray actually originates from the center of the headset. This is another video for head parabolic with the finger pinch for confirmation. So these are all the different selection technique and pointing technique, and we run a user study to compare the performance of all these pointing and confirmation technique. Now, during the study, we recorded teleportation time, we recorded pointing accuracy, number of overshooting, motion sickness through VRSQ questionnaire, and also task load through NASA TLX. And we also collect subjective feedback during the study. For the sake of the time, I'm just going to provide very high-level information about the study results that we found. So in terms of the teleportation time, we found that the head linear and head parabolic was significantly faster than other technique that we explored. And also for the confirmation technique, we found that finger pinch was the fastest across all the technique that we investigated. We also observed that dual is faster than eye blink and voice. Now in terms of accuracy, head linear and head parabolic leads to fewer error compared to gaze linear and hand parabolic. Also, we found that dual lead to significantly fewer error compared to finger pinch, which is an interesting finding, because there is a trade-off between time and accuracy. Pinch was the fastest one, but dual is the more accurate in terms of accuracy. As you mentioned, we collected other different matrices, but I'll directly jump to the subjective feedback. So the subjective feedback is kind of very similar to what we actually found from the data. For instance, the participant, they preferred the head-based pointing as they found it to be stable than other techniques. Also, they mentioned that finger pinch was easy to use and they provide higher level of control compared to other different techniques. For dual, participant expressed that it takes more time. However, they perceive that it offers higher accuracy compared to other different techniques. So from the subjective feedback, we also received very similar comments. Now, based on the study results that you presented very high level, I'm just going to draw some very high level guideline or high level results. So you can say that head-based pointing, both head linear and head parabolic, they offer faster teleportation time and higher accuracy compared to other different alternatives that we examined in our study. This is most likely due to the natural stability that the head provides and also its intuitive alignment with user attention, specifically when they looked at any target. Finger pinch is ideal due to the speed, as we found that it's kind of faster compared to other technique, but just as a note, we also observed that dual is more accurate than the pinch technique. So just to summarize, in conclusion, in this paper, we explored a set of pointing and confirmation technique for controller-free teleportation across varying elevations in virtual reality, where we found that head-based pointing with finger pinch provide advantages over other techniques. Thank you very much for your listening.
Yeah, thank you very much, Halat. Yeah, we have time for some questions. Any questions from the audience? I wonder if you had one.
Hello, Ken Pfeiffer from Aarhus University. So this is a really cool study. We also just recently did a teleportation study, and it's a very interesting topic now. So one issue we encountered, and I was wondering if you thought about that as well, that with gesture interfaces, like you studied with pinching and so on, that you typically use that for normal object selection and so on. And if you, we thought if you replace that with teleportation, that you can't do the normal interactions anymore. There's a conflict between two actions for the same gestures, like using the gestures for teleportation or for object manipulation. And how do you think this can work in future in application?
Can you please repeat the question? If I understand it correctly, the same hand is used for controlling the pointer as well as hand is using for confirmation purposes, or hand is used for commonly interacting with the virtual, other different tasks and so on. Yeah, I think it's a very good question. When even we run the study, we had the same thing, right? Same concerns that how actually user can distinguish between teleportation action and then other different, like for instance, grabbing an objects and so on. So for this particular task, how the hand was used actually very specific way. Hand has to be pointed like this way to teleport the, to activate the race and so on. So probably one idea might be there might be specific like specific action or specific gesture that we can use as a trigger gesture to activate the teleportation ray, and then probably we can make it distinguish from other different one. Like for instance, in virtual world, when you want to grab the object, typically we have a different posture than the posture that we use for teleportation. So there has to be at least some ways to differentiate between the teleportation activity versus other activities and so on. So one idea might be just to use very specific gestures to activate it.
Yeah, I know. Yeah, we also thought about it, but of course that's always difficult. Like it's like with multi-touch. Do you want to learn another gesture? You know, it's like it's really difficult to figure that out. But maybe there's some way to do that.
Yeah, like as I mentioned, that it's a very nice question. We had the exact same concern when we were studying, because like one of the thing is differentiating the teleportation versus other different activities in the VR and how actually we can do it and so on. We did not dip deep into that one, like what would be kind of the trigger for teleportation to other. I think it can be a very interesting study, like designing a study just to see what would be kind of a way to trigger or how actually we can distinguish the teleportation from other different activities, because I'm assuming hand-based teleportation can be one option in the future, like different devices and others.
Well, thanks, but really great study.
Okay, thank you very much.
I have maybe a last question of my own, coming from a similar direction, mostly. So we are also doing studies on this topic, and the problem somehow is when you are isolating the selection process, what differentiates the study from a regular selection study?
Okay.
And how, or the other way around, how do you think generalize your results to actually using teleportation interfaces? Because the usage might look a little bit different, like for instance, it's combined with interaction and stuff like that.
Yeah, I think like it's a very good question. Like for instance, pointing to a general object versus teleporting, like it's a kind of a, like though in many cases, like it's kind of very similar, like specifically if we are using a linear pointer, it's kind of I can actually point it versus I can also teleport it and so on. And this is where all this question actually raises, like how actually you can differentiate from all these different activities, and then like when it would be kind of teleportation versus when it would be kind of navigations and other. I think this is kind of an unexplored space to my best knowledge, that like differentiation and where you can actually draw a line between teleportation versus interactions.
Yeah, I think one big difference is the mental model the user has, right? About I'm moving or I'm selecting, even if it's the same process. But thank you again. We are running out of time. We will discuss that later. Thank you again. Any questions? I ask you to discuss them with them in the Discord. I hope they are online, but they at least brought a video.
Hi everyone, I'm sorry I can't be there. My name's Graham Wilson, I'm from the University of Glasgow, and this talk is about using translational gain to give people the sensation of jumping superhuman distances in VR. And we all know that jumping is a valuable physical activity. It benefits strength, fitness, or just simply having fun. And so research has also incorporated jumping into VR. For locomotion, both horizontally and vertically, for exercise and rehabilitation, or for enhancing the user experience, including through translational gain. But the physical space available for VR experiences is often limited. There are issues of safety for fast ballistic movements like jumping in VR. And small physical jumps also mean small virtual jumps, so it limits the kinds of experiences that people can have. Redirected jumping research has found how we can avoid obstacles in jumping to keep people safe. And translational gain, or amplifying the virtual jump, leads to larger perceived jumps. But most amplified jumping research only measures the imperceptible thresholds, so the smallest amount of gain that you can get away with. This maximizes the comfort of the user as it minimizes the mismatch between the virtual and physical motion. But it also then limits the kind of amplified jumps that participants can have, generally only 20 to 40% bigger than the physical jump. However, overt, so supra-threshold or obvious gains, do work when walking or turning in previous research. They're comfortable, acceptable, and appropriate for use. And so much higher obvious gains could lead to both larger virtual jumps and a more enhanced experience. But we don't know how these obvious gains affect cyber sickness, the sense of the user's control over their jump as opposed to being moved for them, and also the feeling of jumping versus, say, moving through teleportation. What are the maximum comfortable thresholds for gain? So what's the full range of gain that we can use? And what are the thresholds for all three jumping axes, forward, vertical, and sideways? And these are the questions that we explored in our research. The virtual environment we used was a low poly city environment used in previous research, as it provides a good geometric complexity for a sense of vexation or self-movement. The participant would stand in the middle of a long street and then either jump forward down the street, sideways down the street, or vertically on the spot while facing a building during each trial. The jump detection was based on just the MetaQuest 3 headset and the controllers in a similar way to previous research. The jump detection was based on the current headset height versus the baseline height that we calibrated per participant at the start of each study. For each jump, the participant held down the grip button to activate the gain, and then they performed the jump. And only when the headset was above that starting height, the gain was applied to both the X and Y axes. And gain continued to be applied until the headset was at or below the original starting height. Here we see a demonstration of jumping forwards. First of all, with no gain applied, so just at 1 times. And after the trial, the participant would answer a few questions based on their experience just during that trial. Here we see a 22 times amplification, 62, and a maximum 142 times gain, so the biggest gain they could have experienced. Here we see sideways, where participants jumped sideways down the street while facing the buildings for added vection cues, again starting with no gain applied. Now 22 times gain, 42 times, 122 times, and 142. And finally, vertical jumping, which was done facing a large, tall building so that they got vection throughout the entire jump. Here's 22 times gain, 42 times, 102, and 142. For the full details on how we measured the threshold, you can see the paper, but overall we used an adaptive staircase approach, illustrated in the bottom right corner. 8 trials were experienced for each jump type, starting at a perceivable gain level of 2 times. Each trial, the gain level automatically changed based on the comfort of the previous trial. So if that trial was considered comfortable, rated as comfortable by the participant, so rating of 5 or more out of 10, the gain increased for the next trial. If it was rated as uncomfortable, less than 5 out of 10, it decreased for the next trial. The gain would change by a given delta, which started at 20 times based on pilot testing. And this delta was halved in size when the ratings changed between comfortable and uncomfortable, or vice versa. And so it meant that through this, we could hone in on the threshold value for the final trial and take that as the threshold. We used a within subjects design where all jump types were experienced in a counterbalanced order. There was one 8-trial staircase per condition to balance the amount of data we got and the fatigue of participants. The study always started with an unamplified practice, safety, and familiarization session for participants, where they got to practice jumping the 3 ways in a safe and consistent manner. After each trial, participants answered per trial questions in the headset, and we reset both their physical and virtual position. Then after each jump type condition, they removed the headset to answer a number of questionnaires. And finally, at the end, participants were interviewed about the kind of nature of the experience. We only had one independent variable of jump type, forward, sideways, and vertical. And the dependent variables were split across different stages of the study. We had per trial measures on a 10-point Likert scale, where participants rated their comfort, how comfortable they felt, how much it felt like they were jumping, ranging from teleporting to jumping, their sense of jump ownership, as opposed to the machine controlling their jumping, and their feeling of enhancement, so from no enhancement up to superhuman enhancement. There are also various per condition measures, where you can see the paper for details, but these include the maximum comfortable threshold itself, as well as subjective metrics such as exertion, ease of control, enjoyment, and their willingness to use jumping in VR. For full results, you can see the paper, but in terms of the maximum comfortable gain, the thresholds were 107 times for forward jumping, 122 for sideways, and 121 for vertical. So really huge gain levels. And you can see a rough approximation of the virtual jump to the physical jump in the illustration here. In terms of comfort, it remained high across gain levels. In the illustration, you can see gain on the x-axis and comfort on the y, and the vast majority of all ratings were well above the threshold level of the red line. There was no effective jump type on the maximum comfortable gain, and most participants did not experience discomfort at all. They maxed out the gain entirely. However, a third of participants did experience some discomfort at gains ranging from 11 to 62 times. In terms of the experience of jumping and felt like jumping versus teleporting, forward jumping felt significantly more like jumping than sideways and vertical. And for forward jumps, even gains of more than 100 times still felt like jumping as opposed to teleportation. However, for sideways and vertical jumps, the feeling of jumping did decrease as gain increased, but it was still high at around a 50 times gain. For feelings of jump ownership, again, forward was significantly higher than vertical, and there are similar correlations to the previous felt like jumping metric, where the feeling of jump ownership had declined for sideways and vertical motions as gain increased. And then for feeling enhanced, compared none to superhuman, there was no effective jump type with high levels of feeling enhancement across jump types, and the sensation of enhancement increased as gain increased, with a feeling of being superhuman, so kind of crossing that middle line, arising at about 25 times gain and increasing more slowly above that. In terms of the per condition metrics, there were no effects of jump type on any of them. There was overall a low level of exertion across conditions. The realism was fairly moderate despite the large levels of amplification they were experiencing. There were high feelings of safety, again, considering the large jumps. Ease of control, enjoyment, and mastery were all high. And importantly, the willingness to use jumping in VR was significantly higher when gain was applied. So using gain made people much more willing and likely to use jumping as it was more fun or engaging. From their interview comments, participants conveyed that at high gain levels, it started to feel a bit less like jumping. For example, it was like being a chess piece that somebody is picking up and moving in an arc, or it felt like I was thrown, like in circus cannon people, or like a big spring like in the video game Sonic. But there were also significant feelings of being enhanced. So it just gives you more power and control over the jump. Yeah, like I'm a superhuman here. or it felt like I was achieving more. There were also strong feelings around speed and weight. So for example, inside the game I was really light, but my body in real life was quite clunky. Or there was a desire to hang in the air and get that bit in the film where Spider-Man jumps and he spirals his arms as he's jumping. So because our artificial gravity pulled people down as fast as they moved up, it didn't feel quite right and wasn't quite as satisfying as being able to control their descent in different ways. And there are also a range of different metaphors and comparisons for how translational gain felt when jumping in VR. So of course, I did get Big Frog vibes, was one, but also I feel like I'm the Incredible Hulk. So from our results, we produced a number of guidelines. Firstly, high gains of more than 100 times are largely comfortable for all jump types, but a calibration is needed to ensure comfort across all participants. To maximize jump ownership, consider using lower gains of only 20 to 40 times, particularly for sideways and vertical jumps. Amplified jumping can instill a range of player characteristics in the user, including circus cannons, springs, superheroes, and frogs. Jumping under high gain is still considered safe and controllable, which means that smaller physical jumps can still enact large virtual jumps. There are safety concerns over collisions, which mean that we need new boundary tools, as the current proximity-based boundaries aren't sufficient for these fast ballistic movements. And finally, gain can be a strong motivator to perform real jumping in VR. The increased enjoyment and willingness to use jumping could facilitate fun or exergaming. Thanks for listening. If you have any questions or comments or want to talk to me, I'll be on the ISMAR Discord, or you can find me at the email address on the screen just now.